Welcome back. In the previous video, we have seen the emission and we have also seen the governing laws which the emission is been described. So some of the laws studied were the Planck's law as well as Wind's law, Rayleigh-Jeans law, Wind's displacement law also we have discussed. In this session, we will be discussing another phenomenon of the absorption or the heat transfer by the radiation. So the three phenomena that we are going to discuss in these sessions are: number one, the reflectivity; number two, the transmissivity; is the absorptivity. So these are the three phenomena which we are going to describe in this session. So now, in order to understand this, let's consider an example where we have the surface with the surface of S, and then this surface has some area which is actually area of A. And then I'm going to say that the incident ray, which thermal radiation of incident ray is been traveling and falling on the surface like this, and then I'm saying this as G. So the first term that you have to understand is number one, the irradiation. So irradiation means, when you get the thermal radiation here, it will have in the form of the heat flux, right? The radiant energy flux. So if you try to quantify the radiant heat flux per unit area, then it is measured in watt per meter squared, So this quantification is called the irradiation. So the incident ray or the irradiation is ray which is initially falling on the surface. So what will happen when the ray which is coming from some body and falls on the surface? You have to note that this surface is also having an atoms, right? Some atoms here, it's having atoms here. So what will happen is, if I try to write this in very nicely, I will get these rays like this, and then this is my irradiation. So I will say that there are three things it will happen. When this ray strikes on this point, which you can say P, some portion of this G, the total irradiance that you have will be reflected, right? So you can say denote like this, and you can denote like this. So GR is the portion from the G which has been reflected, and then some portion will be absorbed by the solid itself, right? So this portion or the fraction of the irradiation that you have, which is G, which is absorbed in this solid, you can say this as GA, which is the absorption. Then some part of the radiation can be transmitted, which means some can penetrate and it can just go away. So you can write like this: it can penetrate like this and go away, right? So you can say GT, which this is some portion of irradiance which is transmitted. So now what we can do is that if this is the perfect material, then by the conservation of energy, the total number of G that we have irradiance, G equals to the portion of the irradiance which is reflected plus the portion which is transmitted plus the portion which is absorbed. So this should hold true, right? Yes. So now what I will do is I will divide this whole by this total G, So I will get 1 divided by GR by G plus GT by G plus GA by G. So what will you say is that we have a different fraction. So if you consider this one, this is the fraction, This is the fraction of which some rays has been reflected from the total rays. And same things goes here. So what I will do is, I will denote this as GR, So I will say as rho plus this GT, so I can give as tau, plus GA, I can give as alpha. So this tau, alpha and rho, they are the fractions, right? So these fractions are known as, number one, rho. This rho is related with the reflection, right? So you can say reflectivity. So So what is reflectivity? Reflectivity is a fraction of rays reflected to the irradiation, which means the total rays that you have received as an instant ray. The same thing as tau is the transmittivity. So you can say transmittivity. Transmittivity, it is a fraction of rays transmitted with respect to the total irradiation. Same thing, your alpha equals to what? Your alpha equals to absorptivity. Absorptivity, which is equals to fraction of rays absorbed to the irradiation. Right? So these are this VT, you know more. Transmittivity, reflectivity and absorptivity. They are the fractions and they are denoted by the symbols rho, tau and alpha. So how can you remember this? You know this is R, right? So R is started by the rho, then T, this can be started. So tau is started by the T motion. Then we have A, so alpha, you know, is started by this alpha starting is A. So you can remember like this. Okay? So this is very important concept. The next concept that I want to explain you is the regular and the diffused reflection. Consider there are two surfaces here. This is a very smooth surface like a mirror, and this is a uneven surface. So what happens is, this is the point that I'm considering and I'm drawing a normal. Okay, what is normal? This line is perpendicular to the plane of the surface, as well as I want to consider this and I want to draw normal, and I can say this is N and N. Okay, now what I'm going to say is that with the angle of θ1, what happens? Since this surface is very smooth, this will reflect, the rays will be reflected, so you can say G. And then if this is opaque body, which it is, you can say it is silvered much from there, that means our transmittivity will be 0, but absorptivity and our reflectivity will not be 0. So some portion of the rays that we have said GR is reflected, right? So it will make angle of θ2. If this is a very smooth surface, you know it will follow the laws of reflection. The laws of reflection says that θ1 equals to θ2, which means the instant angle will be equal to the angle of reflection. This is called the regular, or you can say perfect reflection. And you can see in this contrary, you know this surface is not smooth. So when you shine in instant ray like this, it will take some uneven angles, right? So if you say θ1, your θ2 will be not equal to your angle. So it does not hold. The laws of reflection does not hold true here, which means that this is rough surface, so this kind of reflection is called the diffused reflection. Okay, diffuse reflection. And these are very important concepts that you have to keep in mind. Okay, now the next thing I want to discuss you about is what are the sum of the laws which governs these three terms: the reflectivity, transmittivity and absorptivity. So the famous law we have is Kirchhoff's law. Okay, so it was formulated by Gustav Kirchhoff. So what it says is that we have to consider a situation like this. Kirchhoff's law. You can say that you have a small body like this here, irregular body, okay, and then this is held with a temperature of, you can say, Ts. So this is the solid body with the temperature Ts, and Ts should be in the absolute scale. Then you can also consider a boundary between them, a bigger body which the smaller body is embedded, such that this between them there is a hollow, but it has a boundary with a uniform temperature of Te. So you can say environment temperature. So what do you say when I say T equals to TA, which means both bodies are in thermal equilibrium. Okay? So in previous class we have learned that if Ts is greater than T, what happens? The body begins to emit radiation towards the boundary or the environment. If Ts is less than Te, then the boundary will emit radiation to the body, right? Because the heat transfer due to radiation is by virtue of its temperature. Now what we can say is that if they are in thermal equilibrium, okay, now I'm considering only for the body. If this is in thermal equilibrium, then my emissive power, okay, total hemispherical emissive power of the body, which I'm saying is E, which is radiation which is originated from the body due to the virtue of temperature Ts, divided by the absorptivity of the body itself. We say absorptivity of the body itself is constant at all T. So this T means this T because they are equal, right? So the ratio of this emissive power, right, divided by the absorptivity is constant, which means it will hold some number that we'll discuss later when we discuss about the law. And this is the statement of the Kirchhoff's law. Okay? Now, let us get a bigger picture of what Kirchhoff's law is. You will be able to comprehend that this holds true. The ratio is constant for this kind of environment where the governing condition that we should have is that these two temperatures should be in equilibrium, which is in thermal equilibrium. Now what happens is that now we are going to consider a case, okay? I'm going to keep this picture and say this one right here so that we can compare at last. So what we can say is, we can say E by alpha is constant. It's the Kirchhoff's statement where all values of T. Okay? Now, I will say consider a body. Okay? Consider a body, small body. A small body Ts. I mean, you can say consider a small body 1. Okay? Having temperature Ts, being surrounded by a bigger radiating body, okay? Now what I'm going to assume is that, see here, at the beginning, my Te is greater than Ts, okay? But at some time T, then my Te dies down and then it becomes Ts after some time T, which is at the time T, it is the time for the thermal equilibrium. During this time, okay, when T is greater than Te, you should know that this boundary held with the temperature of T, E will emit some rays, right? Emit some thermal rays. So you can say that this emission, okay, this emission you can say as EB. Okay, this emission, this is the emission power of bigger body. Okay, now it has emission power of bigger body like this. It will emit towards the body. Okay, now what happens when it emits? Our smaller body, which we denoted as body 1, will absorb the heat, right? So if EB is the emissive power, which means it is the heat radiant per area, right? Emissive power is always radiant flux. So flux is per area, no? So the total heat which my body will absorb will be, just I can say as the total heat which my body will absorb as the instant ray which has been absorbed, like this total ray by the body 1, okay, absorb, right, equals to the fraction absorptivity, which is the this fraction governs the absorption, right? So this fraction is the amount, or by fraction the total, this EB per, and this EB is everywhere like this. But how much of this EB to be absorbed by the body will depend on the absorptivity of the body 1. Therefore, I can say absorptivity of body 1 times area of the body 1 times whatever the emission power the small body gets from the bigger body. Okay? Now, this one as say is a condition 1. Condition 1. Okay? Now I want to change this body into a different body, so that my same boundary is here like this. You can say this condition 1, and then my body is different now here. It's different shape, okay? And it has an absorptivity of alpha 2, and same thing happens. TE and TS. So this EB is all over the body, but all over the body how much to absorb will depend on the alpha 2, as similar to the other case, the previous case. Therefore, we can write like this. For the case 2, GA2 will be alpha 2 times area 2 times EP, which is the condition 2, where this is body 2. Body 1 is replaced by body 2. Okay, so this is the condition that we are getting. Now, once the body absorbs, then what is the energy that the body, our small body, can emit? If we consider the law of conservation of energy, this is the energy that they have got from the body, bigger body, right? So the energy that they can give, if law of conservation of energy is held true, these are the energy that they have got from the bigger body, right? Now, what are the energy that they can give? We have to keep in mind. We have to define that I'm saying my E1 and E2 is the emissive power of my smaller body 1 and 2. So what does emissive power mean now? Now this body, this 1 and 2, is now our emitter. Before it was absorbing the heat, right? But now they are emitting the heat. Yes? So if this E1, is the radiant flux. So what is the total radiant flux they can give? Is E1 times the area 1 and E2 times the area 2. Right? So these are the energy they can give. Equals to, by law of conservation of energy, is the energy that they got. So it should be equal to GA of body 1 equal to GA of body 2, which is equals to alpha 1 area of E raised to B, alpha 1 area 2 of E raised to B. Right? So from here, they are equal. So what can we do here? From here, we know that we can divide this equation and say A1 by E2 equals to alpha 1 alpha 2 times area 1 area 2 times EB times EB. So I can cancel this, and I can also do here. So what happens? What am I getting here? So this is actually what? This is the value of 1. So I can get is E1 by E2 equals to alpha 1 by alpha 2. And I can rearrange this to get what? To get final equation, which is E1 by alpha 1 equals to E2 by alpha 2, which is equals to the constant, which is EB. So G में the G constant. The constant is actually the emissive power of the radiating body, bigger radiating body in the SMA. So I have switched this in two bodies, but this will hold true for every body that you use. Therefore, if I have ith body, if I am doing this experiment for ith body, then I can say is EI is alpha I times EB. This should hold true, where I should be for 1, 2, 3. This should hold true, right? Because any body that you take, 1000, 2000 bodies, this will be going to be true. Okay. Now, consider that these two smaller bodies are black bodies. Black bodies. So, the moment you hear what is black bodies, okay, the moment you say like consider this as a black body, then you have to think that a black body is a perfect absorber, which means my alpha equals to 1. What does it mean? Whatever rays that they receive, they will perfectly absorb all, which means they will not reflect or they will not transmit. So it is 1. Therefore, I can make this, I can switch this, I can modify this equation for the black body, right? So I can say this one, GA of black body 1 equals to, my alpha 1 will be 1 equals to area 1 times EB. The same thing will be GA for black body 2 will be area 1, 2 times EB. Yes or no? By using this, what you are trying to get, you know that they are equal to. These are the energy that they got. So what is the energy that they can give? This will be equal to emissive power of the black body times the area of the black body 1, emissive power of the black body 1 to the area of the black body 2. So by doing this, what are you getting now? You can say, when you divide this, area 1 by area 2, area 1 by area 2 are getting cancelled. So what happens is that, do this, this and this are getting cancelled off, right? So you are getting is EB equals to E black body 1 times area 1, EB equals to E black body 2 times area of 2. And then this area also got cancelled from this. Yes? With this, what does it mean? It means that emissive power of the black body 1 equals to emissive power of the black body 2. Black body 2. Which means you can generalize this for the black body. Every black body will have the same emissivity, right? For this same emission power. So you can treat this as E of the black body. So when you do that, we have emissivity equals to what? Emissive power of the source divided by emissive power of the black body. So you can say black body like this. So what happens? The emissive power of the black body is actually, you can replace from here, right? Because this is true for all, even for the black body. Therefore, you can say EB equals to EI by alpha I. This one. Which will be equal to what? The emission of the black body is that they are equal here. You can say EB equals to EBB 1, EB equals to EBB 2. So from here you can say EBB 1 equals to EBB 2 equals to EB, because they are both constant. So I can say at any, it doesn't matter how many black bodies you take, because with this condition your emission power will be same, which is the emission power which is given by the outside body. Therefore, I can replace this by EB, right? So I can say E by EB. If this is the case, then I have this one, where I can also generalize this as E upon alpha like that, because it does not depend on how many bodies you choose. Therefore, by using this, I have is E divided by what is EB? Now my EB is, you can see, is E by alpha here. So when you use this, my epsilon emissivity equals to E times alpha by E, which is equals to alpha. So we get is epsilon equals to alpha. This is one of the profound findings from the Kirchhoff's law. What does it say? In this kind of situation where two bodies are having a thermal equilibrium and surrounded by a bigger body with the emitting body, with a bigger body, and one body is very small embedded, then the emissivity is equal to the absorptivity of the body. What does it mean? How the comparison of the emissive power of the body we compare to the black body is equal to the amount of the rays which will be absorbed by the body itself. So whatever they can emit, whatever the body can emit is equal to whatever they have absorbed, which means this formula is also based on the law of conservation of energy. I hope you would have understood this video and we will solve more questions in the next sessions. Thank you.